Hey, Caleb Vinica again. So, haven't got around to quoting this product yet. So, I thought today I'd just run through the CAD model and explain kind of my CAD modeling strategy to help you learn how to model something like this. I'm going to be explaining the tools in Onshape. A lot of the tools are very similar to the tools that you can find in SolidWorks. I did take some shortcuts in this CAD model to help me explain this or to get through this faster, but I will show you how I got where I got, and maybe you'll pick up a trick or two. So first of all, you'll see that my feature tree on the left here is organized, and I have features tucked into folders to help me understand where I built certain things. This is something that may not be natural when you first start building in CAD, but as you get a little bit better, you'll find out that it makes a lot of sense to keep features together for debugging. So if I build some features with the lens, it's nice if I can get back to those features and keep them all together. And in this case, what I'm using is a master model multi-body approach. What that means is I am looking at the assembly as though it's a series of parts. So when I get down here, there's actually 21 bodies in my part file. And then I go and expand those out into assemblies and individual part files for further detailing. So this is something that works well when your assembly is lightweight. This I'd consider a lightweight. It's fairly complex. We have 21 bodies here. But almost every part needs to know some information about another part in order to exist. This would be very difficult to build if you tried to build each of these parts independently. I'll just walk you through my thought process. So the first thing I'm going to build is the AAA batteries. They are not unique. I could have downloaded a 3D model for a AAA battery and use that. However, when I'm building a master model, I don't want to use imported geometry if I can. This keeps it clean. I don't expect the batteries to change at all. The batteries' position and orientation is set from the very beginning, and this is kind of the core, the very base feature that my enclosure will need to wrap around. Everything is going to be designed relative to where those batteries go, and so those are the first feature in my tree. It's really difficult if you design an entire device and then you come back and find out, oh, I have to fit something else in here. So if you know it needs to fit, put it right at the top of your tree so that everything can be designed in relation to those features. And the batteries, really, I just created one sketch, and then I did a couple of extrudes, so nothing really interesting here. I did an extrude. I had set the length of the battery at 43, but I offset it by 23. That gives me 20 millimeters in one direction and 23 in the other. And you'll see later why I did that, because, well, you'll see here why I did that. That is because we have a spring on this end of the battery and springs on these ends of the two batteries. And from measuring in the actual device, I knew this was the offset. So that's how I started. Similarly with this one, I did this 43 and 23, but I offset it the other direction. So you can just flip that offset. I'm sorry, you can flip the offset here and here. So if I wanted it to be the other direction, there would be my matching the other ones. So there's my batteries. I did a little boss extrude here and another boss extrude here, the same thing. I'm just using the same features. And I always tell people, don't put fillets at the top of your tree ever, 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 never. However, in this case, these batteries aren't going to be touched again for the rest of the model. And just for aesthetic purposes, I could put this fillet on once I separate this AAA battery out and make it its own part. But I'm probably not even going to do that because I don't need a drawing for the AAA batteries. So I put a fillet at the top of the tree here. I'm not going to reference anything to it. It's purely aesthetic. So avoid that if you can. And that's how I built my AA batteries. The next part, so again, I'm building kind of outward here. The chassis, which is just this extruded part, I can turn it on right here by turning on the eye. This is just an extrude, and I built that off of offsetting these sketch entities from the original sketch and then drawing in a few lines and doing a boss extrude. At this point, it's just a solid block. And I just gave it a depth because I measured the depth on the the production piece. So I knew that it was going to be symmetric, which basically mid-plane in SolidWorks. So it's a symmetric boss extrude. And that's how that works. Nothing special. I then shell it out. That gives me room for battery contacts and terminals. And I did a quick move face because in the actual part, the surfaces, or sorry, the wall thicknesses are non-uniform. And so I brought those two walls inward to align with the actual part. You'll see that the battery terminals are flush with this inside face, which is flush with the end of the battery posts. I did a small little extrude here. This is going to come into play later, and eventually we're going to get rid of this feature, but it was here in the parts. I had to add it. This is a cut extrude through the wall, and it's out of plane. So if this were a molded piece, I would be thinking about this right from the get-go. I'd be thinking about how are we going to mold that feature, and can that molded slot be changed direction? Could we actually extrude it vertically so that the mold can open and close and not have this side pull? I would have been thinking about that right from this first sketch. But again, I'm just modeling a representative feature. I'm not trying to model what I think it should look like. So this is what I'm building, and you'll see in a future design how we get rid of some of this complexity. So here I added a small little tab. This is a locking ear that comes off the end of the chassis and locks into the enclosure. If I were designing this part from scratch, I probably wouldn't have put this feature here because I don't have the mating feature yet. But here, trying to keep all the chassis features together, I was able to measure this on the actual part and put it together. So there I mirror it across the other side. And then I work on some other features. So I'm adding in a little boss extrude. These two little pins are going to be heat staked. So we're going to heat set the top face of these to clamp a little piece down inside of there. So this little piece right here, I'm calling this as part of the chassis. You could have this little piece in its own folder, but I'm just calling it part of the chassis. Ultimately, you wrap the ribbon around this piece and you heat stake these two pins together to lock that in place. And that's just a simple boss extrude. I went 1 millimeter thick with a starting offset of 0.5 millimeters to get it off of that face. And if you look at that sketch, you'll see I just convert entities on these two edges and gave it a 3 millimeter diameter on the slot size. This is a cut extrude because I need to remove these two four faces. So I'm cutting back the chassis. The battery actually, in the center of the device, these rounded tabs are wider just based on the overall enclosure. And again, I have the benefit of seeing this in real life, so I might not have actually put these features at this point in the tree if I were designing it. But this is kind of how it gets built. And sometimes I scroll back in the tree and add a feature because it interferes later in the tree. I mirror that cut back to the other side here. Then I add a couple features, a couple of rounds just to clean it up. Again, that's at the end of my tree for the chassis. So that chassis will get operated on when we do the battery terminals, but other than that, it's pretty much done. That is the internal part. Next, we throw the PCBA on there. The PCBA, from a mechanical standpoint, is purely a placeholder. This part is not used for layout or anything, although it very well can be. Many times I will export a DXF of this top face or export a DXF of this face to my electrical engineer who's doing the board layout. In this case, I just measured what we had and stuck it onto the model. Still trying to build out kind of that core internal features that the housing needs to wrap around. This is just a plain offset from the face, or offset from the front plane at 18 millimeters. That gives me a surface with which to sketch the printed circuit board on. I just do a simple extrude, 1 millimeter thick, nothing special. Then I add a sketch on the top face to indicate where these LED through-hole LEDs are. Again, just visual placeholders. If needed, I could have also done the through-hole holes themselves so that if I export the DXF, I can tell the EE where the holes are, but they're really going to define the through holes. I'm just telling them where I want the LEDs to be placed. I did one sketch on the front plane to help identify this notching feature. And because the sketch is going to be doing two things, it's defining the shape of the push button PCB that faces sideways. It also defines the notches that are cut into the front PCB. Then I use this to first create the PCB. So here's the PCB, and you can see it's interfering with the other board. Then I did a Boolean extract cut or a subtract cut to use the PCB, the button PCB, which is this one, and intersect it with the target, which is the PCB main. Then I clicked the offset button and I picked a bunch of faces here that I wanted to offset. So basically any faces that interfaced with the other PCB. I don't want there to be a gap down here. I don't want there to be a gap down here, but just these faces back here where I wanted there to be an offset. I picked these faces here, add an offset of 0.1 millimeters, and keep the tool. So I want to keep that side PCB. If I scroll back to here, you'll see it. I had two PCBs that are intersecting. I use the Boolean to create the notch, add the gap, and then I do a couple of quick extrude just to show a placeholder for the tactile switch. And with that, we have most of the internal components. There's still a ribbon that comes down through here. I'll add that later. But for the most part, this is done. All right, so that covers the internal features. And in the main body, we have, I didn't mean to do that. We have all right, so that covers the PCBA and the internal features. We drag the rollback bar down. You can see I'm going to start creating some sketches that will drive the main outside aesthetic surface of the device. So I start with a sketch on the parting line of the device, and that is what that looks like. There's two outer edges and two inner edges. So if I just turn these two sketches on, you can see that those sketches are going to help define some of the shapes. I add in another plane that's an offset to indicate, let's see if I can share that. There's the offset. The first plane was the very top. The next plane is that one. You can see that that's where those two planes are. And those come from the dimensions that I'm measuring off the top of the lens. Add another plane and another sort of midpoint sketch. What I'm trying to draw here is kind of the sculpted surface of the device. And finally, a sketch down at the bottom. So this is sort of a framework for the shape or the design. I have the main parting line. It's going to swoop in, come to this point, drop down, and come up for the lens. So lastly, I'm going to create a sketch, which is the side profile. And this is probably the most interesting sketch. But we have the center line. It drops down to this point, which is coincident with that sketch. This is coincident with this sketch entity. We drop down, up and over. I'm defining draft right here as some arbitrary number for now. But this is a driven dimension, so I'm just making sure that I know what that number is. I'm driving draft at the parting line here with 0.5 degrees. So that drives that tangent line right there, which is, so this one's vertical. This tangent line is 0.5 degrees off of vertical, which allows me to drive a tangency between this right here and this line, which is off of vertical. So I can guarantee that this curve will end up with 0.5 degrees of draft once this surface is swept around. So that comes in, it's coincident with this edge and this edge. This one right here is, we're measuring again off of a vertical right here, and that tells me that we're at 10 degrees of draft. I don't have any way of measuring that. I just want to keep track of that and what it's going to be equal to. In this case, it doesn't really matter. This one, I'm putting a vertical line right here, and we're defining that draft angle as a minimum of 3 degrees. So this line comes into that line and becomes tangent. So those two lines guarantee, or sorry, this line guarantees that this line will never lose that 3 degrees of draft at the parting line, or at that bottom of that surface. If this ends up being at 0 or even above 0, we get scuffing, or we get parts that get retained in the mold and can't be removed. So we really need to make sure we understand draft at this level before we detail out any of the parts. And I don't like unconstrained sketches as the blue dot. So arbitrarily, I'm just going to set these two equal to make that a black dot. So everything's black here. That's what I'm going for. And this sketch becomes a surface right here. So what I did is I swept the surface. I swept these orange edges here along this loop path. So there's 4 edges right here that make up that loop. And we now have a surface that basically represents the outside surface of the device. Now, since the outside, the A side primary surface is the most important here, this is what I'm trying to drive. And then if I find out after thickening and turning these into parts, if I find out there's not enough room inside, I can come back and adjust the A side surface slightly, but I'm not leaving the A side up to chance. So if I were to initially draw everything as the B side surface or the inside of the part and then thicken it outwards, I don't have control over the A side surface. And so what happens is the outside looks kind of like an accident, and we don't want that. We really want to make sure that the outside looks intentional, that the aesthetic shapes, the aesthetic surfaces are all driven and controlled, that aspect ratios and proportions are all maintained on the outside surface. And that's really what we're going for here on this part. You'll see this face is white. That's kind of a defect in Onshape. I haven't quite figured this out, but later in the tree, I apply a split and a recolor. And so that face kind of trickles back in the tree. I haven't figured it out, but I'm kind of new to Onshape. In SolidWorks, I would just turn all appearances off and then it would all be gray, but this will work for now. So the bottom surface, I'm just going to do a simple fill, which fills that surface in, and then Boolean attaches all those surfaces together. In SolidWorks, we might call that a knit, but whatever. So this is a Boolean union. We're unioning the upper swept surface with the lower surface. We don't need to keep the tools because we want them to just be one surface. The next thing I'm going to do you can see that's here. This is so the Boolean command, or sorry, so then we do a cut extrude. So that Boolean command turns it into a solid, which is interesting because it doesn't actually indicate that anywhere. We had two surfaces and I put them together, I union them together, and it makes a solid. I don't think that I know exactly why that is at this point, but it is a solid. You can see that it's a solid because it's under the solid body parts field. If I scroll behind Boolean, you'll see that we have two surfaces right here. We have a surface 1 and a lower surface there. So after we do the Boolean, we have no more surfaces left in our parts tree, just solids. Nonetheless, I threw a sketch on the front plane, measuring down from the midline to define this 42 millimeter diameter circle to do a cut through. Now, I didn't know the diameter of this, so I kind of had to play around with it, but I did know that it touched off on this edge and this edge right here, and it also had a depth of 5.6, or sorry, it had a depth of this dimension from here to here. So I kind of just played around with it until, or yeah, I measured from this pin to the depth of this groove, and that allowed me to sort of set the diameter. So this you'll see is a driven dimension. It's not controlled. I'm controlling it to the depth of this cut. That's a simple cut extrude. Then I do the same thing from the other direction. Another cut extrude with another sketch, because this bike light can mount in two directions. You'll notice now that the whole solid is red and some surfaces are changed. This is because I'm in a multi-body part and some of the surface appearances are applied later in the tree. This resolves itself later, so I haven't tried to figure it out. But I'm in the isolate mode. This is kind of an interesting isolation feature in Onshape, but I can go either full transparent or I can have the internals ghosted in at a different level, either a little bit solid or completely gone. I generally just tend to leave it all the way over at the right. I don't like this expand distance thing, but you can sort of like add features back in by physical proximity. I feel like this is very unstable and doesn't ever do what I want it to do, so I just leave this off. All right, so the next thing that I'm going to do is I'm going to take this sketch. I'm going to create a sketch right here using a couple of straight lines that are coincident with this parting line, and then measuring, sort of estimating these dimensions to these curves. I'm saying we got about a 4.5 millimeter diameter, and then we're setting the overall height up to this point. And this sort of shape is arbitrary, but it's close to what the device looks like in hand, so that's where I get the dimensions from. That sketch becomes a surface. So I got isolate on, so I'm going to turn isolate off. That becomes a surface that's going to be my trimming surface for this middle body. Next, I need some tools to work with to help create this sort of raised section right here. So I do an offset surface, which is nothing more than just a copy. I'm copying this whole outside rim, and I'm setting the offset to 0, so it becomes a copy surface. In SolidWorks, we would just call, if you set it to 0, it actually changes the name of the feature from offset surface to copy surface. But anyway, this is offset surface at 0. Then I take the transform tool, which has in it a copy in place option. And now I have 2 copies of this surface. I have one that's shown and one that's not shown, so I can hide it. See, one has the upper area included and one does not. The next thing I do, and this is kind of the shortcut that I took. I don't know if this is the best way to model it, but it works. So what I did is I moved the face of this lens upward by up to this face right here. So I said all the way up to this face. I want to make sure that we're all the way up to this face. And then I did a thicken using a remove command. So I took the surface that was the outer surface and the lower face with a step in it, and gave it a thickness of 2 and removed it from the system. So what you're seeing now is what's left of the enclosure. Again, if I isolate this, you'll see that we now have that step in the enclosure, just like we wanted. I realized I stepped past one option here, and that is, I talked about creating this surface and this offset surface, but then I also did a mutual trim in here, which, if you look at a mutual trim, what that is you're allowed to section or select which sides of which surfaces and how you want to keep them. And then it sticks them together if you click this merge command right here. We have surface 1, surface 2, and I'm able to change that. So if I flip this, I can keep the bottom side of that surface, or I can keep the bottom side of this surface, or the inside of that surface. So I could create the inverse of this that way. But what I wanted was this face. What I got was that face. I did a move and a thicken remove. So thicken remove is a command unique to Onshape. I haven't seen this in SolidWorks, but it's kind of interesting. And if I click keep tools, I'll get left with that surface still. I might need to use it later in my tree, but in this case, I don't want to see that surface again. I'm never going to use it again. So I just hit keep tools and remove it. So now I have the step in the enclosure. Now, here's where I start breaking some rules. I generally say don't put any fillets on your model until later in the tree. And for some reason, and for one reason I did here, and that is because I was going to apply a shell. If you apply a shell and you have an internal or an external round, it will calculate differently than if you have an internal shell without an external round. And in this case, the external round is small enough that my internal round goes to 0. But just making sure that I had that round in there to allow it to calculate, I put those rounds onto the device. And here in Onshape, a shell is called just a hollow if you don't have any open faces. So I just hollowed the whole thing out, gave it a thickness of 2 millimeters. And then the next thing I did was use that internal shell to Boolean subtract a couple of little corners off of my chassis. So this little corner, here's my tool, is my new shelled outer. My target is my chassis. I offset it by 0.5 millimeters just to make sure that all those little corners and details get cut off. So if I click on it, you can see that it actually cut off the corners of those little parts, and it left a 0.5 millimeter gap around the inside. Kind of a hack move on here. It also cut a face off of this unit here. And I say it's a hack move because I don't love it, but the chassis component is completely non-aesthetic. It's purely a functional part and it must fit. So it works. And in the end, the chassis part is going to go into another file and will be detailed out for molding. So this way we will know exactly what that absolute maximum volume has to be. Here what we did is we glued on this end body right here. We're doing a union where we glue the chassis and this part and this part. So we have the main body, that little tab, and that little tab. And we're gluing them all together. Now we have a new chassis. Or yeah, a new body. So that part, actually, we could probably move that Boolean up in the tree. But the reason that it's down here, just to explain, the reason that I did this Boolean glue at this point and I left these two off was because if I dragged this Boolean feature where these are glued anywhere up in the tree before here, what happens is, well, one, it might break, but two, the body is going to cut off the ends of these two S hooks. And I need the S hooks to penetrate into the wall because I'm going to create a notch later in the tree where this clicks into. So if this Boolean feature 16 were any higher in the tree than right here, these two interfaces or interfering tabs would be removed at that point, and I don't want that. Okay, so that's the main body shape. So at this point in the model, I have the main outside surface defined, and I have the main internal features defined. But they're not really well detailed yet. They're just close enough. And I think I'm feeling pretty good about it. So let's start on the button. The button is a very complicated little switch, and it needs to interact with this tactile switch on this PCB here. Now the button, if I just look at the sketch first, I was able to take some dimensions off of here and throw all these things in here. So 1.7 millimeters. I just estimated all this. Took a few measurements of the top dimension and the lower dimension and guessed on some of the overall stuff. But now I have a sketch that I can use to do an extrude. And what I'm extruding is just two surfaces. So those two surfaces come all the way through the part, and those are going to become the inner and outer edges of my button surface. Next, I need a few more tools for trimming. So I offset the inside surface by 1 millimeter into the body. And then I offset the outside surface 0.5 millimeter into the body. And these are measured directly from the part, but these are two trimming surfaces that are going to give me some tools to better define that surface. So here's what I did. I took the outer, which is the main body here, and I want to split that part, and I want to split it with this inside tube surface. And I'm not going to keep the tools, but I'm going to keep both sides. So the split does one thing. I'm going to hide this by pushing Y. Now we have this little chunk of meat or plastic separate from this whole body. So if I click that and click this, you'll see that we have two bodies. One is red and transparent. One is gray. And if I hide the surface, it'll be even more clear. Okay, so now we just did a split using this tube surface and this main body. We did not keep that tube surface, so the tube surface goes away, and now we have a split out solid that's perfectly coincident with the outside surface, or the outside body. The next thing we're going to split is we're going to use the outside tube surface and that newly formed outside solid. We're not going to keep the tools, but we're going to keep both sides. Now if I uncheck this, I can pick whether I want to keep the inside or the outside or both, but I want to keep both sides because I need both of these solids. All right, another offset surface. I use offset surface quite a bit here because I'm building a very complex little button, which looks really simple. I do a move face on that inside button surface. So again, this is a solid body. It looks transparent just because of some appearances that are applied. But that's a solid body, so I can move the face outward. And I just use a direct editing model tool called Move Face. I just moved the face 0.5 millimeter outward. The next thing I did is I used the faces. I split all of these faces on the sides of that body, and I split them with one of these offset faces from earlier. So this is the offset face that's 0.5 millimeter back from the outside surface. You can kind of see it there. It is surface 2, so I turn this one on. And let me just do a section view, maybe it'll be more clear. Okay, so we have these two surfaces inside of here. And I'm splitting the faces with this inside face here, with this orange face here. The next thing I did is I convert entities, and I created another sketch, which is just these things because they're going to create the notches in the face of my button. And then I delete face all of these outside faces on this center body, which converts the solid into a surface. It says leave open. So now if I identify, or let me just isolate this guy, you'll see that this is now just a surface body because I deleted the face on that. So this used to be one of the bodies. If you remember, this came from the two tube surfaces that I cut out from the main body. And then I did a delete face on the front, so now I'm left with the surface body. And if you look closely, remember I'll actually roll this back. So here was the solid. I did a split on these inside faces to create some geometry because I needed this edge right here. So that was the split. And then I created the delete face, which now essentially creates the ability to have this edge inward recessed from this edge. And then I create 4 boundary surfaces. Now, if you're not familiar with surfacing, boundary surfaces are pretty straightforward as long as you have 2 controlled inputs, maybe even more. But these are really simple boundary surfaces to calculate. So we have an inside edge and we have an outside edge. And then I created 4 fill surfaces to fill the corners. Now, right now, this is just a bunch of, this one, edit. This last one here says merge with all. And when I merged that last surface, it became a solid. So if I drag this back here, I still have a bunch of surfaces. This is still a surface, surface 3. But once I put this last fill right here, now I have a solid. So this is a little bit different than SolidWorks. SolidWorks, I could knit the whole surface together and be left with the surface. But in Onshape, as soon as I knit the surface into the other surfaces, it becomes a solid. All right, so now this Boolean, remember I just built this little body out of surfaces. And now I'm just going to knit that body or consume that body into the other body, and I'm left with a single body. And you might wonder, why didn't you just do a chamfer all the way around the edge right here? Well, the chamfer tool is for or really general conditions. And in fact, I would try it. I want to say I tried it here and it didn't work. I could try it here again. In fact, I'll try it live just to see how it works. And if it doesn't work, you will know why I chose to go this route. Okay. Okay, here is the challenge. Chamfer command works sometimes, and a lot of times it doesn't. But what I needed was a uniform bevel all the way around the button. And if you look at what the chamfer command is calculating, it's taking 2 millimeters, or sorry, a 0.5 millimeter step in on this edge, and a 0.5 millimeter step in on this edge, and then it's going 2 millimeters back from this edge in this direction. Now, if I change it to offset, it won't build at all, unfortunately. So if I change it to tangent, I can get it to build, but it doesn't look right. And if you don't see the difference between this chamfer and the chamfer that I just built, well, then I guess you won't understand why we had to go to this much trouble. But using the boundary and the fill guarantees that we get a clean chamfer of uniform chord length. I don't know if you'd even call that chord length. Uniform length, uniform spacing, and it's a very crisp, clean geometry that I can easily control. So throwing in a little bit of cleanup geometry, and then this is kind of a fun one. So in order to punch those, punch the notches onto the button part, so here's the button part. I need to combine it with the housing, and I also need to put some notches inside the front face. But the notches can't just be a straight boss extrude. The reason is because they need to follow the front curve of the button. So following the front curve of the button means that we need to do extrude, right? And then I'm going to use that one surface that I created, which is this one. This surface is offset back from the face of the button, and I'm going to use that surface to split and remove the back sides of these boss extrudes. So what you see here is a split. I'm not keeping the tools. Again, if I keep the tools, it just saves the surface. If I keep both sides, I'm gonna be left with a whole bunch of bodies I don't need, so I'm gonna turn that off. And this surface becomes the back surface of my 3 little bodies here. Now I have 3 chunks of material that I don't need, but I'm going to use those to Boolean subtract and create these 3 notches in the button. Now if you look carefully, you'll see that there's nothing square about these. They're all tapered top to bottom, and they're tapered along, or they follow the backside. However, there's going to have to be a tool or a mold that pulls these features. And so to do that, I'm actually going to add a draft right here and open up those faces so that a tool can get in there and pull out those directions. Now, in this case, I believe that the draft is more of an aesthetic than a functional requirement because the draft is pulling through a TPE material, a rubber material. And so we don't need this much draft, but it adds to the aesthetic and improves the look of it. So that's what those look like. This fillet or round right here, again, not necessary. I could add that at a later part detailing phase, but because I'm the only one working in this CAD file, I'm going to be doing all the work downstream. I'm just going to add it right here. All right, the next thing is we're going to split the back side of this button using this entity to split, which is 2, which was a surface offset from the inside of the part. And the reason I'm doing this, we're going to keep both sides. I'll show you in a second here. We now have this body and this body. I'll isolate those. Now we have a button that's 2 layers thick. And the reason I'm doing that is because I'm going to The reason I'm going to do that is I need to offset this button body and I need to cut through it. So here I'm using edges of that sketch and I'm cutting through and I'm creating this hole on the back of the part. So again, isolating just these two. I created this cut, I split out the center, and I did a little move face. Now I'm going to boolean those. I'm going to boolean that. So this little move face right here and this little split allows me to create a notch. I want to just isolate this one single body here. There. So what I've created here is the sort of surface that the button sits in. Because the rubber button is actually not full thickness. So in order to create this face right here, which is part of the rigid plastic overmold, I needed to first create that one surface, split the button in half, and then attach that body to the main enclosure. Hopefully that makes sense. Next, we put a small extruded body in here, and we add that to the button. And then I do two sketches. I do one sketch which is going to follow this outer edge of the button. And I do another sketch to indicate that this is a little peg of rubber material. And then I do a curve-driven pattern to make those pegs follow this curve so I can get little pegs all the way around the button. There's my curve-driven pattern. So now the pegs are running all over the button. Those actually are mechanical fastening for the overmold. So what I need to do then is cut them off because they're not actually going to be that long. So I do a surface offset from the inside of the part. I only offset at 0.1 millimeters, but then I use that surface to split and cut off all of these little pegs. So once that surface offset is created, notice the surface offset has a hole in the middle. We're going to use that to split off the surface, and got kicked out of my isolate. So now that surface, which looks like this was my surface that I used for trimming. So here was my surface for trimming, and I use that to trim and split off and cut all of those pegs. So if I change this, or if I roll the split forward, I get booted back out of my isolate because that body doesn't exist anymore. I'm going to go back to isolate this guy, and that's the back of that looks like. Now the final step then is to run a Boolean operation on this button body and let it remove every bit of interfering material from the main housing. So we are Boolean subtracting the button itself from the lower overmold, which is the main housing name at this point. It may be kind of confusing that the names are following some of the bodies that don't make sense. This is kind of a, I suppose, a glitch or something in Onshape where my names actually didn't come into play until much later in the tree. I didn't name these part numbers and names until later. And now when I scroll back in the tree, sometimes it grabs some of these names and associates them. So you kind of have to ignore the names until the tree is resolved all the way at the end. But here we're keeping both bodies. We're keeping the main enclosure and we're keeping the button. And that is how we did that. So if I just isolated these two, you'll see that the button has removed itself. These are now coincident surfaces. And those little pegs stick just through the surface by 0.1 or 0.5 millimeters, just through the inside as part of the overmold operation. And that's the main body. So now I have the main body and the button. And let's just roll a little bit farther forward to how we split off the lens from the main body. So this one is probably the feature set that needs the most help for improvement. I don't love the way this is done, but it's quick and dirty and it shows the mold complexity, which is really all I'm after in this case study. So the first thing I did is I took that surface, which you just saw, which is that blue surface, and I'm using that surface, which was developed much further up in the tree. I'm using it to split off the lens. And as soon as we split off the lens, I don't need that surface anymore, I don't think. So I'm just going to hide it. I could actually absorb it here, but I'm wondering if I might actually use it later. So I'm not going to change that right now. So I do a split. That allows me to split off the lens, and now I have two separate bodies that are touching each other right on the parting line. But that's not realistic. We actually don't have that. So I do a quick move face on the inside to intersect these two parts. And then okay, so this is where I'm using that surface again. So I'm using that surface, that same blue surface, so I didn't absorb it. And I'm using it to split the lens, and I'm splitting off this chunk that was interfering. And then I did a move face on the chunk. So I split it off, now it's two bodies. I move that face over, and then I move this face over, and I'm left with something that I can then throw a little bit of draft on and create this little tab that interferes. Now, I don't actually like how thin this feature gets, and so I may come back and resolve that or fix it later. But with a quick Boolean operation, I can add some clearance on the Boolean, and now I have a lip groove that follows the entire bottom surface of the lens all the way around the part. So if I isolate this body, missed it. So if I isolate this body, you'll see that we now have a lip groove that follows all the way around the part. And if I isolate this guy, you can see we have a groove that runs all the way around the body of the part. So again, I don't love the way this works, but it is moldable. And if I were building a clean manufacturing model, this is not the method I would take. In fact, there's one spot where the lip groove goes to 0 thickness right here as it transitions up this ledge. And I don't like that at all. So I would want to fix this for production. But generally, thinking through this, my goal here is to build fast CAD that gets me approximations of the complexity for tooling so that I can start to have discussions about where we can remove cost. If I hyper focus on every little detail, I'm not getting to that end goal. I'm focusing on the cleanliness of my CAD model, and I'm not able to learn what I need to learn. I could spend a week trying to improve the slip groove, and it wouldn't improve the cost at all. Okay, so that's how we split out the lens. If we drag the rollback bar down into the main seal, we created a sketch on this plane and created a boss extrude up into the part. That creates this little cut right in here, because I know that there's a small gap in there. And then on the bottom surface of that cut, I created another thin extrude. So I'm just, or sorry, a solid extrude using that same sketch. I'm using it to cut back this surface so that we can create the gap between the upper and the lower parts. Next thing I did is I created a sketch here using some offset geometry and boss extruded up with a small offset of 2 millimeters and a depth of 2 millimeters using this only operating on this body to create the notch for this to pop in here and lock in place. Now this is a very thin wall right here. This may be an area of concern for manufacturing or for mold filling. So this would be something I would want to carefully understand and look at before we ever release parts for manufacturing. But over here, a local thin spot on this big of a body would be just fine. So the next thing I wanted to do was create kind of a little notch right here. So what I did is I took a plane and I split off this top face of my newly created body. So if I roll to here, and then I can just move the face in because it's a separate body. They're not showing as separate bodies here because they're the same color. But I can just move that face inward. And I can move this face inward because there's a small little gap on here, and this is going to be part of the main seal. All right, so now we're gonna move on to this aligner, this yellow part that's up top. And this is the part where I believe that we don't need this part at all. I think it can eventually be deleted, but it's in here, we need to get it quoted. And so I need to create that geometry. So a simple sketch, a simple thin extrude. I don't need to go into detail there. The bottom surface, so if I roll to here, and I isolate this guy. See, this is all this is. So it's a thin extrude for the outside, a thin extrude for the inside. And then I create a sketch on that plane where I'm gonna go ahead and draw one of the screw bosses, and then I'll do some mirroring to push it around. So what I did is I created one sketch entity which shows the inside screw clearance, the outside screw head clearance, and then the outside of the boss. And then I also defined it relative to two construction geometry lines, so that I can use those to help me mirror this feature. So then I do a couple of extrudes, all using the same sketch, so I don't have to redraw geometry, but I can do the cut where the head goes through. I can do the cut on the bottom where the boss is going to come up into. And then I do a boss going down. So I'm going to aligner and chassis, isolate these two. So then I put in this one, which is the boss going down to the chassis from. So I went all the way up to the part, which is up to the chassis. You see the chassis highlighted there. we're merging it with the chassis, and it's got its draft applied right at the base level. So these are all the features necessary. And then we go and do a mirror. And what I'm doing in the mirror is I'm clicking reapply features. If I don't reapply features, things break because it doesn't know that you need to go through and do all the extrudes. It's trying to apply the features to things that already exist. So you can reapply the features and mirror it that direction. And then we'll mirror it the other direction. Oh, in between there, I did a cut extrude and just cut off the end of this unit because we don't have a unit there. So there's the updated chassis. And then I went through and added some draft to it because it was interfering with the lens a little bit. And it needs draft anyway to be moldable. So there's the chassis aligner. Now, one of the tricks on this part is that there's a rubber bottom in here where this entire bottom surface is made out of rubber. And right now, the only thing we have in here is a solid plastic bottom. So how are we going to show the manufacturer that this is actually an overmold? So to get there, I'm going to add a plane down into this region, and I'm going to make a sketch on that plane. Now this sketch, I'm using some offset geometry, and what I'm doing is trying to, because I'm worried about the final A-side surface, this is another shortcut. I don't recommend this at all, but when you're in a hurry, sometimes you do things that are wrong. So here I referenced some fillet edges, and I'm doing it partially intentionally because I want this surface to maintain the same curvature when we're done, and I want the rubber to be referenced to the edge of that fillet. So there is some intentionality here, but I don't like generally ever referencing to the edge of a fillet. But what I did here is create an offset surface, and I offset it 0.6 millimeters. And then I use that surface, or that sketch, to extrude a surface into the part itself. So that surface is just extruded. It's orange here in this body. And I'm using it to just go all the way through the body. Then I did a mutual trim where I had surface 1 and surface 2. And surface 1 came a long time ago. Surface 2 is right here. And we're doing that to create a surface that looks like this. We're basically making a little tub. Once we have the little tub, we can use that to make a split. And now, if we look at our section view, we can see that we now have two bodies. And there's no gap between them because the surface doesn't have any thickness. But now we have two bodies. We have a millimeter of rubber and a millimeter of plastic. Now the plastic's pretty thin. I don't like how thin that is on the bottom, so I'm going to thicken that up a little bit with a move face on the inside. And then we're going to move face and thicken up the rubber on the outside. And this is a couple of reasons why we're doing this. We're going to add a little bump on here. So if you look closely at the part, you can see that there actually is a small shutoff surface right around here where the mold closes down and pinches off against the plastic and the rubber fills up against there. So I can actually feel the edge of this rubber, and this is an accurate representation of what that overmold looks like. But also it gives me a little bit more thickness here on the part, and we now have that rubber overmold with just a few features. So a matter of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 features. I could create that rubber overmold that matches the bottom surface, matches the design intent. Now the lower lid needs to stick onto the lower enclosure. And to do that, we have these small little latches here on the side. So I created this sketch, just taking some dimensions, and I intentionally intersected those sketches with the wall of my part. So here you can see that the part, or the sketch, is intersecting with the upper wall where we're going to have a notch, and the lower wall down here where it's actually going to become part of the same body. Here I slipped in a thicken, I guess. I don't know why I did this here. But I thickened just the face of this boss extrude to create the plastic backing of... So right here, this gray piece is a rubber seal that seals up against here. But on the back side, this thicken command creates a lip of plastic that will get added to the main enclosure. But you'll see that when I did a thicken, it thickened in kind of a weird direction and it made a small sliver. I don't like the sliver, so I just push this surface down with the move face. And we will connect those together shortly. Okay, so this extrude I did with a depth of 6 millimeters, but an offset of 11. And that's because I measured 22 millimeters from the inside to inside on these two parts. And right now it's a separate body. And then I mirrored it across the two axes to create 4 of these copies. So if you look in the tree right here, you'll see 1, 2, 3, 4 of those examples. And those are all just there. Just for kicks, I want to see what shows up. See, everything shows up here. I don't want the chassis to show up. I just want the lower enclosure. But anyway. Then I do a Boolean combine to combine all those together. And now I'm left with just this guy here. So I have the inner lip. I have these tabs. And I have the lower surface with its notch cut out for the rubber. All right, so I made another video about the pad printing. I'm not gonna go over again how that works. I'll just scroll through this area here. You can go and look on my channel for how to create this pad print, but it's basically a sketch, a split line, another sketch, another split line, and I'm able to pad print those logos onto the surface. And now the coloring is back the way it should be. The hooks, which are on the side of the device, these are for where the O-rings snap on and connect it to your bike. There's 2 versions. There's one that's closed for retaining the O-ring and one that's open. And I just do a really simple boss extrude and then mirror those on either side. These are not difficult. I created one sketch. I did a thin. I added it to the body. It's 1.5 millimeters thick. It's depth of a math equation, 21.4 divided by 2. And I'm sorry, that's the offset. And it's a depth of 8 millimeters. I'm merging it to the upper enclosure. That's how those get created. Now, there is a little tab opening feature on the side that's not super difficult. There's just a few extrudes, so I'll just scroll through that. I don't see anything interesting here, but that feature is here if you want to go and see. I did a sketch on the side, an extrude out to that face, and another sketch from the top view showing kind of a coin-sized device. I did a cut right here. Extrude cut, and then some rounds. That's it. Nothing complicated. The ribbon is extremely simple. It's just a spline that I drew around all the parts and did a thin extrude. So that's hidden inside there. A couple things I'd like to cover though, the battery terminals, and let me hide some stuff here. All right, so here's the ribbon. Now the battery terminals, nothing really complicated about the battery terminals, but I created one sketch and then I created these two surface or solids and I Boolean subtracted them using an offset. Now I didn't offset anything on the bottom surface, just the outside surface to give me that gap around them. And then I created this sketch on the outside. The next thing I created was a helix coming off of that plane to help me draw where the spring was going to land. And helix is a really straightforward feature, but I first created this using a surface. I extruded it 6 millimeters tall. Then I applied draft to that surface from the neutral plane to give it 8 degrees of draft. So that surface is right there. And then I used the surface to define a helix. By number of turns, I went 4 revolutions clockwise. Again, this is just representative. I don't expect any manufacturer is going to use this geometry, but it gives me an idea of how much space things take up, and it gives them an idea of what parts and features we need to do. I did a sweep using that surface and a solid. Created a copy, moved it over. This is something unique to Onshape. I can transform and copy things by make connectors, and the make connectors can be implicit. So when I picked this make connector, I really just picked the center of this face and it populated its own make connector. So if I say from make connector, I can just pick this edge right here and it will automatically create that make connector for me, even though it didn't exist before. And then I can delete this make connector over here and say, well, I want it to go over here. And I can just pick this edge and it'll recreate its own implicit make connector. I could have it copy it to here if I wanted. All these implicit sort of centerline features, really neat. I can just do that. Pick that center, and now it will copy that over. Then I did a series of Booleans and extrudes and cuts, and these are not interesting or unique, but going through a bunch of extrudes, I got all the way to here, and I now have some tabs that come over the edge. These are not difficult. You can figure out how to model something like that. But what is interesting is that there is a couple of wires, and my friend Evan Reese came up with this wires feature script, which I think is really cool. So to build the wires, I needed to create a line or a 3-dimensional sketch curve. So what I did is I created first a spline curve that goes from in one direction, from this line to here. And I kind of had to play around with this curve. I haven't actually even fully defined it yet because I might move it. I don't know. But that's one sketch. Then I created an extrude from that sketch, which is just a surface. And so where that surface goes is where the wire edge is going to go. Then I created another sketch in a different plane. So this one is on this plane. And that shows me in this plane where my wire is going to start and where it's going to end. And I always want to make sure that that line is continually or completely enclosed within this surface, because I'm also going to extrude that as a surface. going in the other direction. And now I have my two X and Y orientations of my 3D spline curve. And I'm just going to use one of them to split the other. Now I have an edge. Now my edge, if I circular pattern that edge around, because I have two wires, now I have one on each side. And I can completely control those by the splines, by the way. Then I use this really cool feature script called wire, and the wire just looks for an edge, any kind of edge. And I can plug in, hey, it's a 22 gauge wire, the wire diameter's 0.64 with insulation thickness of 0.3. It's a black wire, by the way. I can pick other colors. And I want to strip the ends 2.5 millimeters. Boom. Now I got a wire, and it looks appropriate. It follows my curve, and it's perfect. Like it's for visualization purposes only, but that allows me to tuck that wire through that gap. And I can do the other one with the other side. This one I'm going to do as a red wire. Interferes a little bit with the chassis right there. In real life it doesn't, but I don't need to worry about that for right now. And then I delete the two surfaces and I'm just left with the wires. And I can go ahead and do a cut extrude from where those wires penetrate the board to create the hole that will then be fed to my electrical engineering team to build that circuit board. So that's sort of the complexity of this type of a design. I think you could build something like this if you step by step work your way through it. It's not terribly difficult. It just takes some time and some understanding of the tool sets. And so hopefully this is helpful. If you have any questions on complex surfacing in SolidWorks or Onshape, or any type of master modeling question, happy to help you out if I can. Thanks.